Okay, what we want to look at in this example is we want to think about having a box on a flat surface, and we want to then have like a rope attached to the box and then pretend that someone is pulling on the box, so there's some force of a pull. Now, when we're looking at having let's say the force is applied perpendicular to the flat surface of the box. So when we do this, that means the other force is on the box. The force normal is up from the ground. There's a force of gravity down. And so we can then sum up our forces on the box. So when we look at the forces in the y direction, we sum the forces in the y. That equals MAY. And the two forces acting on the box in the y are force normal minus the force of gravity equals MAY. And we know that AY is going to be 0 because we know that the box is not flying up or not burrowing into the ground. So AY is 0, so that tells us that the force normal minus the force of gravity equals 0. And when the sum of our forces is equal to 0 here, this is the condition that we call equilibrium. So the box is in equilibrium in the y direction, and we get the standard result that the normal force is equal to the gravitational force. So the ground is pushing back up on the box as hard as gravity is pulling it down. Now the next part that we have to look at is we have to sum the forces in the x direction, and when we sum the forces in the x direction, that has to equal the mass times the acceleration in the x. So when we look at all the forces in the x, we see that we only have the force of the pull in the x. So this has to be equal to the mass times the acceleration in the x. And we can then know what the acceleration of the box is in the x, because we can take the force of the pull divided by the mass of the box, and the box will experience an acceleration in the x that's dependent on the force of the pull and the mass of the box. So if your box has more mass, the acceleration will be less for the same pull, or if you increase your force of the pull for the same mass, the acceleration goes up. So this is our standard pulling on a box, and we assume that the floor we're pulling on, the surface we pull on, is frictionless. So we have this situation. Now let's change this up just a little bit and look at something else. So we're still going to have our trusty box, because they're so easy to use. But now let's assume that you attach the rope, and when you pull, you're going to pull up. Hopefully you can see this at some angle theta. So when we're looking at the side of the box, the rope is attached and you're pulling up on the object. So it'd be like having the rope over your shoulder and you're pulling the object behind you, and that rope makes some angle theta up towards you. And so the idea then is you have some force in the y. You have a force, this is the force of your pull, the force of the pull in the y, and then this is the force of the pull in the x. So we'll call it Fty and Fx. So you have to now break the force of your pull into your components, because you're pulling at some angle. You're having the box behind you and you're trudging along, pulling up on the rope. So what does that tell us? What does that do to us? And we'll still assume that our friction is surface. Our surface is friction. So we have the force of the pull going up at some angle. We still have a normal force normal up, and trusted gravity is always pulling us down. So now let's take a look at what's going on. So let's sum the forces in the y. And we always know that that's MAY. So when we sum the forces in the y, what do we have? Well, we have our normal force, force normal up. We now have a part of the force pull plus force of the pull in the y, and we have a force of gravity down. So we have minus gravity. That equals MAY. Now again, we don't have the system is in equilibrium, the box isn't flying up off the earth, nor is it burrowing into the earth. So we always say that AY is 0. So the force normal plus the force of the pull in the y minus gravity has to be 0. So this condition where we have the sum of the forces equal to 0, that's equilibrium. So the box in the vertical direction, this way, is in equilibrium. It's not experiencing a change in motion vertically. So what that tells us, in this case, how hard is when we look at the normal force? The normal force is the force of the weight of the box minus however hard you're pulling up on it. So the normal force in this case, if we put in the rest of it, would be the mass of the box times gravity minus the force of your pull times the sine of the angle you pull. So the normal force, as you're pulling up on the box, the normal, as you would pull up and trudge along, that normal force is actually less. The ground is working a little bit less to push the box up because you are helping decrease the amount of normal force because you're pulling up on the box. So the normal force is working a little bit less than it has to because you're being generous. Now let's look at the sum of the forces in the x direction. Well, when we sum the forces in the x direction, that's equal to MAX. And when we're looking at the sum of the forces in the x direction, we only have one force. That's the force of the pull in the x, and that's equal to MAX. So when we look here, this is only one force, so that means the box is going to start accelerating this way because of our force of the pull. And the amount that the acceleration of the box will be FPX divided by the mass, or in this case it would be the force of the pull times the cosine of theta divided by the mass. So basically, as you adjust the angle of your pull, if you're taller or whatever, however you adjust that angle here, theta, that adjusts the acceleration of the box in the x direction. And you can also see that angle also affects the force, the normal force in the y direction as well. Okay, so we've pulled up on, we pulled the box straight, we next pulled the box up a little. The last case we need to look at is we need to pull down on the box. So let's look at pulling down on the box. So we'll keep using our trusty box here. Okay. So what we want to do is we're going to attach the point I, and we want to pull down on the box. So now we're attaching and we're drudging along, but we're pulling down on the box. So you can imagine the rope's high and we're pulling down on the box. So here's the forces on pulling. And you can now imagine if you're thinking of you're using a thing and we're pulling down on the box. Our rope makes some angle theta, and that gives us two components. Again, we've got an x and a y. And depending on where you want to make in, if you make it there, then you have your FP sine theta in x. You have FP cosine theta in y. And that's what we're going to end up having to look at equine angle. Now, if you choose what's called this angle over here, theta 2, if we use theta 2, then you have the FP cosine of theta 2 and x FP sine of theta 2. So you can use either angle, you can either measure it here or but it doesn't matter which way you want to measure it from. It's probably actually safer to measure using theta 2, and even if they give you the problem, it's safer to measure the force of the pull using that theta 2 because it sticks with the convention that we use. So that would mean that the force of the pull cosine of theta 2 and the force of the pull sine of theta. And that would be our Fx, Fpx, and our Fpy. So we'll use that convention because that's the standard convention that we use. But you could always use the other one if you want. So what else works on the box? We have the force of the normal minus the force of gravity. So when we go to sum up the forces on our box, what do we have? We have some forces in the y, some of the forces in the y, and dy, as we always do. So when we sum these forces in the y, what forces do we have? We have a normal force of, we have minus Fpy, because when we're pulling down on the box, we have a force from our pull in the negative y direction. That was the force of gravity. Just as it's been so many times before, our box is not going into the ground, or maybe a little if we pull hard like that. But our box isn't moving up or down so much, we're going to call it equilibrium. AY is going to be 0, so that way will be somewhat forces. Say that the sum of the forces is 0, we have equilibrium in the y direction. So this tells us now that the force of the normal is the force of the pull in the y plus the force of gravity. So the normal force has to work even harder because not only does it have to support the box, you're also pulling down on the box, increasing how hard the normal force has to, how much force the normal has to apply to keep the box on the surface. So when we're looking at this becomes force of the pull times the sine of theta 2 plus mg. So you can see that the normal force has to work a little harder because you're pulling down towards the ground. So this is the normal force going on. Now when we sum the x, the force Fx is equal to max, and we're going to get our pretty much standard result. There's only one force on the thing, it's the force of the pull of the x equals max. And when we're looking at that force of the pull, then and we're going to know the acceleration. The acceleration is the force of the pull of the x divided by the mass. And this turns out to be Fp cosine theta 2 over the mass. So we're basically, whenever we're attaching just one rope to our box and we're pulling it along, there's about 3 ways you can do it. You can pull it so that the rope is flat and you're pulling it straight. You can attach and pull the rope up, or you can attach the rope low and pull up on it, or you can attach the rope high and pull down on it. Those are the 3 cases we looked at on a frictionless surface when we're pulling a box. So what usually happens is in the Y you have equilibrium, the sum of your forces is 0. It just affects how you're pulling the box, affects how hard the normal force has to work. And then in the X direction we'll have some type of acceleration based on the force of the pull and the angle. So this is kind of looking at pulling on a box under three different conditions.